All right. Oh, we're doing it. We're live. We're live. Oh yeah, I didn't do the right title. I'm an idiot. Meeting 4. Save. Perfect. Let's actually end it. Alrighty then. This here. Sorry, I just gotta shuffle some windows around while I'm here. Voice. Perfect. Oh, I forget that. My friends got banned from this server. I forgot. Oh god, I'm reminded.
RIP.
RIP is for real.
Who all got banned? I know you mentioned it was like Harm. Was it
Harm,
Devin?
Tim, Mason, someone else. I forget. Mushroom.
Devin is okay though. Devin didn't get banned.
Yeah. Alright, we're live on YouTube. We are live in screen share. I put the link to the stream for now. Yeah, I don't know. A couple people got banned. I don't know. It's kind of disheartening because there's a lot of people in there that like really help the community, and I think what ended up happening was like maybe they were all like. I think because they all got banned at the same time, so I feel like everyone was in a channel at the same time, and maybe like some bystander witnessed some like real talk or some like joking around that might not have seemed like joking around depending on if you were new to the group chat. You know how like sometimes we rag on each other a little bit? I think they might have like witnessed that and reported it, and then everyone just got banned. So I don't know, man. Weird. But it is what it is. Life happens. So here we are. So last week, I think, did y'all meet up with Rubric and chat about adapters, right?
Yeah.
All right, good.
Yeah.
So you did that. You chatted about adapters, and you found out that adapters are nothing more than just a way of like kind of converting the interface of one thing into the interface of another, right? So if you have an application that like speaks one way, you can use an adapter to make it speak another way or to expose it to something else. So pretty cool.
Yeah. Oh, actually, I think I did have a question on that.
Yeah.
Because we were discussing it a bit last week about whether or not an adapter is just sort of like a more specific use case of a sidecar, if you want to describe it like that, or if like it's usually specifically something else. Because it seemed like the sidecar was sort of generic, and then like an adapter is just like you said, being used for a specific like taking some data out of it and like transforming it or whatever.
Yeah, I mean, you can run an adapter as a sidecar, but you can also run an adapter outside, like not as a sidecar. So again, right, like...
Okay, yeah.
Yeah. These are just like patterns. So when we talk about sidecar, it's really yeah, go ahead.
Okay, so the pattern isn't like the way the containers are constructed, it's like the application, or that's what it's describing, more than like how you organized it. Okay.
Yep, exactly.
Because that's the thing, like they're all sort of described as patterns, but it's not like, oh, this is like a network or like organization pattern and this is like an application pattern. They're just sort of like patterns, so I wasn't sure.
It's really just distributed systems patterns, right? That's really what it is at the end of the day.
General.
Yeah. The sidecar is really just a way of like saying, hey, run these two things like next to each other so we get those benefits. The ambassadors are like, hey, run this thing on my behalf so I don't have to like talk to that service directly. I go through an ambassador, right? And the adapter is like, hey, kind of translate me from one interface to another, right? Or vice versa. And generally, ambassadors and adapters run well when they're close to the application that they're serving, right? Yeah. And generally that means putting them on the same node with each other. You know, that way the latency is really low and blah, 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 blah. So,
co-location.
And that exactly, co-location. And that's why those sections are introduced in the part 1 single node patterns. That's why they introduce it all as a part of the single node patterns, because
Right. Yeah.
that's generally where you'll see those patterns in place. But it's not a hard rule either. Cool. Oh, I should have did my little intro. Yeah, this is a book club. We are reading the Designing Distributed Systems book. It is available for free on Microsoft's site because I believe they like sponsored this book. So that's why I'm streaming it on YouTube, so that way we could read it together and see it together. We're not like reading it live on the stream, but we're just going through the chapters, and we are on chapters 5 and 6 today. I messed up when I put the thing in the Discord chat saying 4 and 5, but really I meant 5 and 6, so I'm really sorry. So if you haven't read chapter 6, that's perfectly fine. I'll just talk about it today, and you can like read it on your own time. It's not a lot of pages, and it makes sense once we go through chapter 5. So part 1 of the book was single node patterns, right? We covered those: sidecar, ambassador, adapter, all of that. We're going to move off of that now, and we're going to move into part 2 of the book, which is serving patterns. So instead of having everything on a single node, now we're going to start talking about like what sort of patterns do we look at when we use multiple nodes, right? And the author introduces like microservices here, the term microservices. And he also introduces the term monolith. So the author describes a microservice as a system built out of like many different components that are running different processes and communicating over like these APIs that they've defined. Whereas monoliths are just putting all the application functionality into like one single application code base. And that's kind of the difference, right? Again, these are the author's definitions. Are they going to be the official definitions you see everywhere? Maybe not. Maybe so. Depends on, where you're at. But I think this figure shows the difference between microservices and a monolith pretty well. In a monolith application, you have like one application running, and inside that application, there's different like functions or different code paths that execute the logic you want. And it's very tightly coupled. So if function A needs to talk to function B, it's a very tightly coupled interface here, right? And in a microservice pattern, you break those things out into different logical groups. And each of those microservices communicate with other microservices over a well-defined API contract. Okay? The author kind of lists some of the benefits to this out. And he basically says like some of the benefits to breaking a monolith out into a microservice, like two microservices. It like provides you the ease of focusing on a single service. And the idea is to have like these smaller, more focused teams that just focus on those microservices, rather than having to know the whole monolithic application in your head and having to load all that context. You can just focus on the microservices that matter to you, right? And they call this like the 2 pizza team. And all that means is like a team that's small enough to be fed by 2 pizzas, right? 2 8-slice pizzas. That's really all they mean by that. So if you ever hear the term 2 pizza team, that's what it means. Like 3 to 4 people, right? Maybe 3 to 7 people, depending on how you eat pizza. Cool. And then breaking a monolith down into microservices also forces you to like define these little API contracts between each microservice. So instead of having like a bunch of functions that call one another that are very tightly coupled, you define an API contract between microservices, and now you're able to like change the implementation of the microservice as long as your API contract is the same, right? And also like when you break a monolith application down into microservices, you can scale each microservice independently of one another. So if microservice B is the microservice that gets like, super, like if that's your bottleneck and that gets stressed under load, you can just scale microservice B up without having to scale up microservice A, C, or D. In contrast, if you're in a monolith application, if function B is like being overloaded and it needs to scale up, you have to scale up the entire monolith, right? So you see some of the benefits there, and those are fantastic benefits, but they don't come for free. The downsides are that the system becomes more complex, right? When you have more microservices and you have to deploy them and manage them, that introduces complexity. Complexity also comes with cost of maintaining, cost of like monetary cost of actually, spinning all these things up. And then also cost of debugging. It's harder to debug a distributed system because not everything is on that same, not everything's in that same application, right? You can't just open up a debugger and step through your service, because now you have multiple microservices running on different nodes in different places. So now debugging becomes more difficult. Cool. And then with all of that in mind, the author basically says, that's what monoliths are, that's what microservices are. And let's start talking about some of the patterns you can use to have distributed systems on multiple nodes, right? So we're going to talk about multi-node patterns that you can use for your distributed systems. And the author makes a point really quick to say, the patterns that we're going to talk about in part 2 are not mutually exclusive. So you don't just have to use one pattern and then you can't use the other. You can kind of mix and match some of these patterns to get some of the benefits from them, together. So we'll see that when we talk about sharded services in chapter 6. Cool. Let me just share the YouTube stream real quick. That way the people that did get banned can join in.
Oh yeah.
Oh man, banning, fun. Okay, cool. All right, so let's move in. So chapter 5 is the first one. Let me lower this a little bit right there. So chapter 5 discusses replicated load balanced services. Does anyone have, so I'm pretty sure everyone read at least this chapter. Maybe you all didn't read chapter 6, but I think everyone read chapter 5. Does anyone have anything to say about chapter 5 or any questions or anything they want to talk about?
I have just one basic question that's not even chapter 5. Is there the naming convention for naming images is the owner name / the project name?
Like for containers?
Yeah.
You can name them however you want, but generally the full image goes into a registry, like an organization, and then an application name, right? So docker.io / sudomateo / application1, right? That's generally how it goes.
Gotcha. Thank you.
And then each of those images can have a tag associated with it. So I can have docker.io / sudomateo / application1 : 2.0, right? That's my version 2.0. Or : 3.0. That's my version 3.0. So you have tags as well. Cool. So if there's no questions, I'll just walk the chapter and kind of talk about what the author's saying here. So load balancers, right? Load balancers are a very critical part of distributed systems. Actually, they're a pretty critical part of any system, really, because there comes a time where your service can't handle the load that it's being given, and you're going to have to scale it up or scale it out, okay? Or we call this vertical scaling and horizontal scaling. Vertical scaling can only go so much, right? You can only give so much memory and CPU to a system before you just reach physical limitations, right? Not every motherboard out there can take more than X number of RAM or X number of CPU. So you have to scale up to an extent. But if you pass that, you need to start scaling out, okay? And this is where load balancers really shine, because load balancers allow you to have multiple nodes of your application running, and they can route traffic across them using different methods, right? There's round robin, or there's session stickiness. Round robin is hey, server requests to this one, then the next one, then the next one, then the next one. And then when you run out of nodes to serve, you go back around, right? So if we're all sitting at a table and I'm passing you forks and knives, I'll give a fork to you, a fork to you, a fork to you, a fork to you. And then when I reach the end of everyone at the table, I'll start from the beginning and give everyone a fork again. Same thing with load balancers with round robin. And then stickiness basically says hey, give similar requests to the same backend node again and again, right? Stick it, have it sticky to that node. We'll talk about that in a second. Cool. But in order to load balance your application, you have to know the data that your application is using, right? Or you have to know a bit about how your application works. And your application generally is going to fall into two like types. You'll have a stateless service and you'll have a stateful service. Okay. Stateless services are just applications that you run that don't require any like persistent or saved state to operate. And you might be asking yourself, like, wait a minute, don't I have a database? And I'm like, yes, you do. You have a database. What I mean by stateless services, or what the author, or what we all mean by stateless services, is the code itself that you're deploying, right? Your Express app, or your Go app, or your Rust app, whatever. The code that you're deploying, that doesn't have to hold state. It can reach out to a database or can reach out to something else to get its state, okay? So when we say stateless applications, we really mean the app itself does not hold state, right? Cool. So if you have a stateless application, you can scale that stateless application outwards. You can horizontally scale it so that you can route requests across your nodes and share the load, right? So if you have one node for your application and you've scaled it as high as you possibly could and you've reached its limit, well, now it's time to scale it out, right? Because now that's the only way you'll be able to get more throughput or more load through your application. And you don't have to reach like the vertical scaling limit before you decide to scale out. You can scale out earlier for other benefits, okay? I'm looking at the GIF. Share the load, yeah, exactly. Cool. So this is the basic architecture of a load balance service. And it's really important to know that I think the author mentions it right here. Yeah. So this highlighted section here at the very top, if you want to put a load balancer in front of your services, every server that's behind the load balancer, or every node or application, whatever you want to call it, they need to be identical to one another. And they all need to be capable of handling traffic, right? And this is a very key concept. They need to be identical to one another. That's a key concept of load balance services. If they're not identical to one another, you get yourself into all sorts of trouble. So for example, imagine I'm running this image here, right? I have a load balancer and 3 application servers behind it. If 2 of these application servers were running version 1 of my app and one of them was running version 2, I've just put my system in a very non-deterministic state, right? That's bad, because as traffic flows through my application, depending on what node it hits, it can go to version 1 of my application or version 2 of my application, and that sucks, right? So the application nodes behind your load balancer need to be identical. That way you're giving your users the same level of service. Now, I will caveat this by saying there are times where you do want to deploy different services behind the load balancer, like canary deployments or whatever, but we'll leave that out for right now. So just keep that in mind. Cool. When you have these stateless services and you want to put a load balancer in front of them, you generally want to put a load balancer in front for 2 reasons. One is so you can handle more load, right? There's only so much you can do as one node, so you need more nodes to handle the load. And for 2, for availability or redundancy, right? If you have one node for your application and that one node goes down, you are now completely down, right? You're 100% down. If you have 2 nodes behind a load balancer and one node goes down, your application is still up, right? It's still running. You might be on a degraded performance because your throughput might lower a little bit, but you're still up. So you use load balancers generally to handle more load and to have higher availability. And the author discusses that we talk about availability in terms of like 9s, right? Like 99% available or 99.9% available. 9 availability. Yeah. Let's see if this works. Is there like a SLA calculator? Yeah. Okay. Cool. I think I brought this up another time. But if you have a service that is 99% available, that means that you are allowed 14 minutes of downtime per day. Okay? Your application can be down 14 minutes every day, and that will achieve you 99% uptime. Or every year, you can be down for 3 days, 14 hours, and 56 minutes. if you want to be 99% available. Okay. And this might sound great for like most things, right? Because honestly, the reality is most applications out there, most companies out there, they can afford to like be down for 3 days in a row, and nobody will know, nobody will care. But this is not true for bigger companies, right? Like the Googles and the Amazons of the world, or even the financial companies, right? If your bank was down for 3 days in a row, that would suck, right? So in order to increase your availability, you use these patterns that you're discussing in this book to help. So what does it look like if you wanted to add a 9 to this, right? 99.9. Well, if you wanted a 3 nines service, we call this a 3 nines service. If you want a 3 9 service, now instead of being able to be down for 3 days a year, you can only be down for 8 hours a year, or 1 minute, like 1.5 minutes per day. That's what you're allowed to be down with. Can you do that? Can your application do that? Maybe yes, maybe no. If you wanted to do 4 nines, you can only be down for about 1 hour every year, or about 8 seconds a day. Can you do that? And if you wanted to go to the 5 nines, which is very difficult, you're only allowed to be down 5 minutes for the entire year, or about 1 second a day. So you can see how like having a single node for your application makes these very difficult to achieve. And this is why these patterns in this book are very important, because it helps us achieve this availability. Okay. And you as engineers in your company, or maybe owners of your own company one day or whatever, you need to determine what your SLA is, service level agreement. That's what this stands for. You need to know what your service level agreement is for your applications. Are you going to be a 2 9 service? Are you going to be a 5 9 service? But know what you're signing up for, right? As in whatever you sign up for, you're going to be bound contractually with whoever signs up for your systems. So cool. I just want to show that. And that's what the author's kind of talking about here, right? He's saying like there's 3 nines and blah, 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 and this and that, da, da, da. And he's saying it's almost impossible to have something 3 nines or better, because that means, like, for example, if I put 3 nines back in here, that means you can only be down for 1.5 minutes every day. And if you're deploying your application every day to a node, I guarantee you it takes longer than 1 minute and 30 seconds to deploy your application. So by definition, if you have one node and you just wanted to deploy your code to it, you're already breaching your SLA, right? Load balancers come in and allow you to now have your app fronted by a load balancer, and then you can do a rolling deployment across them. So if you have 3 nodes behind your load balancer, you can take one out of the rotation, deploy the new code to it, put it back into the rotation. Then you can go to the next one, take that one out of the rotation, deploy the new code, and put it back into the rotation, and do the next one, and do the next one, and etc. Now your application is up the entire time, but it gets upgraded. So you don't lose any availability, and you get these benefits. So any questions there? That's called horizontally scaling your application. Any questions on that? Sweet. And horizontally scaling your application is really nice to do when your applications are stateless, meaning they don't hold any state themselves. They get all of the state that they need from their database or from Object Store or from anywhere else. Awesome. Very nice. Your front ends generally are pretty stateless, generally speaking, depending on what your front end is. But if you have like a static website, it's probably very stateless. You can just throw like 5 copies of that service behind a load balancer and you're good. You're scaling horizontally and you're good, right? You have good availability. Cool. Your application, the load balancer doesn't just magically know that your application is ready and up to be serving traffic, right? So your load balancer has what's called like a health check or a readiness probe to determine whether or not it should send traffic to your backend node. And that's just called usually a readiness probe or a liveness probe. They're kind of different in Kubernetes, but we kind of speak about them pretty generically, so you might hear them discussed like similarly. But all this means is your application, like a well-designed application, should have like a health check or a readiness probe that it should like, when I hit that readiness probe, you should return me like a 200 HTTP status code to tell me, hey, I am ready to receive traffic, open the floodgates, right? And that's all this is for. And that's useful so that when you are deploying your applications behind a load balancer, the readiness probe will fail until the application is actually up and ready to serve traffic. And then once it passes, the load balancer will be like, oh, you're ready? Let's go. So make sure you're designing your applications to have this readiness probe, especially if you're going to throw them behind a load balancer. Cool. And then the author goes on and just shows you how to like create a replicated service in Kubernetes. I don't have any examples ready for you today because I've had a busy couple of weeks, and I'm so sorry. I'm starting a new job soon and my last day is tomorrow. So I've just been a little busy. But the author deploys a 3-node like pod, right? Or 3 replica pod here. And he puts it behind, I think, a load balancer. And it's just a dictionary server. And you can see that he deploys 3 replicas of it. And then he throws a load balancer in front of that dictionary server. And that's a load balance service. So since there's 3 replicas behind it, traffic will go to any one of those 3 nodes. Cool. I said before that load balancers have different algorithms that they can use to send traffic to the backend. The most common algorithm is round robin, where you just kind of go in order, and then when you hit the end, you loop back around and go in order again. But sometimes that's not beneficial to your application. Sometimes you'll want to do what are called like sticky sessions or session tracking, right? A very good example of this is imagine if you logged in to a website and it stored like a cookie that kept you logged in, and it stored that cookie in your browser, and then on the website itself it stored its like tracking of that cookie in memory, right? The group's not closed. We're just going over a book club, so you're free to hang out and chat, Sam. So yeah, imagine you have that web application, you log in, it gives you a cookie, and then on its side, it's tracking your cookie in its memory, right, somewhere. If you send another request to this load balance service and you happen to get routed to another backend, well, now your cookie doesn't mean anything because that new backend doesn't have the tracking part of that cookie in its own memory, right? It doesn't know what that cookie means. So you'll be prompted to log in again. And then if you send another request that happens to get routed to another service, you might have to get logged in again. So sometimes it's useful to do what's called session stickiness or session tracking, so that each client that connects through the load balancer gets routed to the same backend node repeatedly within a certain time frame. This is called session tracking or session stickiness. Okay? And it means that like these 3 people that want to use the service, this red guy, he goes to the middle node, this middle girl, she goes to the first node, and this green dude goes to the right node. And they always go there because that's what their session has like stuck them to. And that might be useful in your service as well. Any questions on why you would want to do like sticky sessions or session tracking? Kind of the same idea.
Makes sense to me.
Cool. All right. Now the author goes into not just like load balancing at the network layer, right? Because you can do load balancing at the network layer, but now the author starts to go into like application layer load balancing and replication. So previously, this load balancer that's fronting these applications is more of like a network load balancer, right? It takes TCP or UDP requests and like forwards them along somewhere else. Okay? But you can actually do load balancing or replication at the application layer. So like layer 7 in the OSI model. And this enables you to do some pretty cool stuff. And one of those things that you can do is you can introduce caching into your code, right? So if your code needs to like hit a backend database to service requests, that's going to take some time, right? Because making a request to like if I make an HTTP request to your web server and it goes through the load balancer and hits your backend, now your backend receives that request, and in order to get the data to like serve that request, it needs to hit the database. Well, that's going to take a long time, right? Because hitting the database, getting a query, and getting the result, and sending it back up, that can take some time. You can actually put a caching layer in your application, like in your architecture, to reduce the amount of time it takes to serve these requests. And the author shows like an example of that, and he says like instead of instead of just using a load balancer, you can throw a caching layer in between your user and your backend service, and it can cache certain responses and results so that it can serve them faster again and again and again. And that's really it about caching. That's all I really wanted to say there. I think, let me just see if there's anything here that I wanted to cover. Yeah, I think reading the math here is pretty cool. So what the author is basically saying here is you want the fewest number of replicas for your cache as possible, with like a decent amount of cache per replica. That way you don't have to duplicate the cache across the replicas too much, right? Because he's basically saying like if you have 10 replicas with 1 gig of cache each, you would actually probably want like 2 replicas with 5 gigs of RAM each, or 5 gigs of cache each, because 2 times 5 is still 10, 10 times 1 is still 10, but when you do 2 times 5, you only have to store the 5 gigs twice, rather than storing the 1 gig 10 times. All right, so like putting cache on each replica, that's where it like, you know, it can get expensive. So anyway, the math, like looking at the math behind it is pretty cool sometimes.
Question.
Yep.
So in that case, is the trade-off essentially, so the fewer caches you have, the more you can store in that cache, but then you have like less fallback or whatever? Like, why would you ever have more than 2 or like 1 or 2 caches is my question, I guess.
You will see the answers.
Like, would it be like geolocation stuff? I think I remember
that too.
Something about that.
But you'll see more of the answers to that in the next chapter when we talk about sharding.
Okay.
Yeah. But in this case, right now, he's just saying like, try to stick with fewer numbers of caching servers that have a little bit more cache than many caching servers with less cache, because you have to copy the cache to each node, and it's less expensive to copy things to fewer nodes than it is to copy it to many nodes. That's all he's trying to say here. So that's really all he's like saying at this point.
Okay.
Okay, so then he gives us a kind of like the finalized diagram once we've added a load balancer and caching to our application. So we have 3 application nodes fronted by 2 cache nodes in front of it, and then fronted by a single load balancer. So user requests come in, they hit the load balancer, they get routed through the web cache. If the web cache has that result already in it, it'll just serve it automatically, right? And then the request is done. No need to hit the backend app servers because the cache already had it loaded and it sends it. That's called a cache hit, right? That's a cache hit. If the user request comes in, hits the load balancer, goes to the web cache does not have the page cached or whatever it is cached, has to hit the backend application service, and then that backend application service has to hit the database. That's a more expensive, right? It takes longer. That's called a cache miss. Okay, so cache hit and cache miss. Those are important terms to be aware of. And this is kind of the setup that you'll see. Cool. The author gives a little bit of hands-on here. So that dictionary server that he just deployed, those 3-node dictionary server fronted by a load balancer, he adds a cache server right in front of it. And now you're able to have like user requests come through the cache and then hit the load balancer. And then that increases performance. Cool. And that's really it, I think, for this chapter, right? I think there's like a couple more things here. Yeah, a couple more things. Any questions so far on like why you would want to use caching? Or load balancing. We can talk about that too. Sweet. All right. So now that we have a load balancer, now that we have caching, let's see other things that we can do to help increase our reliability and such for this distributed system. So one thing that you'll probably have to run into in your life is rate limiting and DDoS attacks, right? Or denial of service. You can't just spin up a web service, throw it behind a load balancer and call it done, because you're going to get people that are going to do bad things to your service and they're going to kind of be, jerks about it. You're going to have to build in rate limiting, right? So you're going to have to limit the number of requests that users can make per second. So that's something that you should think about. And then same thing, you do rate limiting also to help prevent denial of service attacks. If you gave me access to your web server and you said, hey Matt, I deployed something, it's on the internet, I can just start hammering it with a bunch of requests, right? And I can bring your service down if I do that. So you'll want to think about how to rate limit your requests and how to best prevent like these denial of service attacks. This book doesn't really cover like how to do rate limiting, but we'll talk about it. So rate limiting, generally, you'll have some sort of service or some sort of middleware layer that you have on your application. That middleware layer will keep track of the requests that people give it, right? So if I'm coming, if I'm an IP address, 1.1.1.1, if that's my IP and I hit your service, you will keep track of my IP address and you'll say you just made one request. The more requests I make, you'll like increment that counter and you'll be like, you made 2 requests, 3 requests, 4 requests, 5 requests. And you'll do that again and again and again. And then you will use that information to deny me if I make too many requests in a given time frame. That's basically the high level of how rate limiting is performed. Again, there's more elaborate ways to handle that and more other considerations to take into account, but that's the high level thing, is you kind of keep track of requests and you look back a certain number of time and you see like, hey, did this user make more than 30 requests in the last minute? Yes. Send them 429. Start denying them. I'll wait for the Neon to finish typing this question.
No, it's not important. I'm trying to meme. Hold on.
Oh, that's fine. That's fine. Keep in mind too, you don't just want to rate limit every single person ever, right? You generally want to give a low rate limit, is low rate limit make sense? You want to give a low request per second limit to people that are not authenticated. And then if you do authenticate to your app, meaning you're a valid user, you generally give them a higher limit, right? Like if you're all familiar with GitHub rate limit, you can see that GitHub, like they have documentation about it, but basically, let me see if they had it in over here. Yeah. If you're unauthenticated, you can only make so many requests to the GitHub API, but if you are authenticated, you get a higher request limit for the API. So just keep that in mind. Cool. I thought they had better docs for this, but I guess not. Whatever. Doesn't matter. My face went Cloudflare. Yeah, Cloudflare. Yeah. It happens, man, sometimes. Another thing you want to keep in mind is TLS, right? And I'm not going to say SSL because SSL is, old school. We don't really talk about that anymore. But TLS, Transport Layer Security, it's what gives you the S in HTTPS. You'll want to keep in mind, like, who's going to terminate your TLS connections? Is it going to be your load balancer? Is it going to be your caching layer? Is it going to be your web layer? Like, what's going to actually terminate TLS connections? You have to think about that, because whatever needs to terminate that needs to now have TLS certificates in order for it to be trusted and whatnot. So just keep that in mind. The author says, like, you'll just want to think, all he's really saying here is, like, just think about where TLS termination is going to happen in your setup. You might have to deploy something to do TLS termination. And in this case, the author deploys this diagram here where he has HTTPS requests go to a new Nginx service. That Nginx service routes back to the Varnish cache and goes through. But then non-HTTPS requests, they just go directly to that Varnish cache and go down. So you can do something like this if you want, or you can do something else. But something in your application stack, in your architecture, will have to handle SSL TLS termination. Cool. And the author chooses to do that with Nginx, which is perfectly fine. Most modern load balancers can handle TLS termination, so that is kind of like a built-in thing. And I think that's it for this chapter. So any questions about load balancing replicated stateless services? This is a fun chapter because it starts to show you that, like, oh wait, I don't need just one app running. I can have more instances of my app running, and I can start load balancing them and doing things.
A question for, I guess, the caching layer in particular. So in this case, I think the example he uses is a what was it? You said veneer or
Varnish, yeah.
whatever the varnish, the HTTP proxy or caching service or whatever.
Yeah.
Is it like, I'm assuming this pattern, like, you'd also apply it to something like your database, so you could use like something like Redis or whatever as
Yep.
like your cache, and then you apply that. Like, you can basically do like as long as you have data or you're serving something, there's probably a service that you can use to act like your caching layer.
Yep.
And this is like the pattern would just apply essentially, like you have your containers set up with those sort of middlewares to do that.
Yep. It'll look something like this normally. Is exactly what you're saying. This red thing is probably Redis. This red one is probably Redis, and then the database down here is Postgres. But you'll have your app server. A request will come in. You'll check the cache for that data. If it exists, you just boom, you're done. Send it back. If it doesn't exist in the cache, that's a cache miss. You'll fetch it directly from the database, right? Get it from the database, store it in cache, so that way next time you have it, and then send it back to the user. So that'll be a cache miss.
Yeah. So another question, I guess, in like how your applications interact with the cache. So obviously, like, if you're working with a database and, you know, somewhere in your application you allow a user to like change their password or change their email or something, they can't just change it on the cache, right? So does that mean like any sort of like writing operations, if it's like a database, you always end up like passing that stuff directly to your database, and the caching is just there for like any reads, like, and like the more common reads there are, like they'll show up in the cache more or whatever. Does that make sense?
Yeah, things like that, things like password changes and all that stuff, they don't even go to the cache, right? Because those are like critical application things. They have to go to the database. I'm talking more about like an API where you fetch like the latest, I don't know, Pokemon cards from your Pokemon API or something, right? Whatever API you have.
Okay. Something non-critical that like it'll get updated, like, right? The cache will get updated at some point, but it's not like critical that you have, like, that you always have the correct item like right now.
Right. Yes, exactly. And generally when we speak about cache, there's like two main patterns you use with caching. There's one that's called the cache aside or lazy loading, and you can read about that on this. I'm not going to go into that. And there's something called like the read through, write through, right? Depending on if you're doing a read operation or a write operation. And there's that pattern too. I linked it in the chat for you all so that you can see it. I guess I'll put it on the YouTube chat because, you know, I'll be a nice person.
It was lazy loading and write through, right?
Yeah, I put it in the chat, this link, so you can just read through it. But these are different caching patterns that you can use for your application, right? And then what you touched on is like having out of date data and stuff, right? There's a possibility, and that's where you would kind of go back to the CAP theorem a little bit. I don't know if I think we pulled this up in one of the things. But the CAP theorem is like three principles that you can have where you can have there's three of these things, choose two, right? Choose two of them.
Yeah, I remember that.
Yep.
Yeah.
So you can either have consistency, meaning every client sees the same data all the time, right? Your data is always consistent. If all of us are hitting the same API and someone uploaded a new photo, a consistent API would be, as soon as I upload this new photo and you all tried to read it, it's there for everybody. That's consistent. Availability means all clients can retrieve data even if it's outdated, right? So if I like put a record in our database and I say like the value is foo, and then I go update the record to the value bar, and you try to read that record right afterwards, you might get foo back or you might get bar, depending on the consistency of the system. But availability means I just need the data to be available. I don't care if it's partially out of date. And this is where caching kind of can hit you, right? Because if you cache a response to a web page or something, and you cache the response foo, and then I go get that web page again, but it really has been updated to bar on the back end, but your cache still has a valid entry, your cache might serve you a stale entry, right? So your system is available, but it might be out of date. It's not consistent. Okay? And then there's partitioning, meaning the system works as expected, even if there's a network like failure or a network outage, right? In this CAP theorem, partitioning is a given. You have to account for partitioning because networks are unreliable and you just can't tolerate anything else. So you have to always support partitioning. So you're really just trading off between consistency and availability. So keep that in mind. Cool. One random question. How quickly does the cache update then? As quickly as you can update it. Generally speaking, when you put data into the cache, so let's go back to this one. When you put this data into the cache, so your application gets hit with a request, it has to go to the database to get the actual data, and then it stores it in cache. When it stores it in cache, it's generally given an expiration timer, so it doesn't live in cache forever. It lives in cache for a certain period of time. Like I'll say, hey, cache this for the next 30 minutes, right? And the cache will cache it for the next 30 minutes. And then once that, if it doesn't read from cache again, every time it reads that thing from cache, it'll update the timer, right? So basically, if I store the value foo in cache and I say, hey, cache is for 30 minutes, and then 5 minutes pass and I read the value foo again directly from cache, the timer will reset because I've read it, right? That could be a way that you do it. But if I don't read that foo for 30 minutes, it'll get expired, get removed from cache, and then the next time I need to read the foo key again, I have to go back to the database for it. So that's how like caching kind of works. You can manually expire things in cache to force cache invalidations. That's what it's called, like cache invalidations. There's like memes about this. What is it? There's 3 hard like problems in computing or something like that. I think it's this one. Or 2 hard things.
Oh, I think I've seen this one.
Yeah, and like there's only 2 hard things in computer science: cache invalidation and naming things or whatever. Cache invalidation, this whole thing that we're talking about, this distributed system stuff with caching and all of this, these are very hard problems to get right. Because when you do it one way, you're going to hurt a certain subset of your users. But if you do it another way, you're going to hurt a different subset of your users. So there's never a perfect answer here. If you say like, every time I deploy my application, I'm going to invalidate my cache, well, then now you're going to hurt performance because you're going to force a cache rebuild every redeploy, and that's expensive. But if you don't invalidate your cache, you can serve stale records to your users and give them out-of-date information. So it's all a matter of like what availability and consistency trade-offs you want to make. So, cool. Jacob put the example of high availability, low consistency, I think is YouTube likes. Exactly. That's a very good. YouTube likes chooses availability over consistency. If I go to a random YouTube video right now and I like it, and like let's say the YouTube likes are at 900, and if I like the video and now it's at 901, if you view that video, you might still see 900, right? Because it doesn't matter that the like count is consistent. It matters that it's available. And I'll put the thing up. That's a very good example. Cool. Whereas consistency is more important probably in your bank account, right? If I have $1,000 in my bank account and I withdraw $500, well then I want $500 to be leftover balance. I want that to be extremely consistent, because then if I go withdraw another, $500, now my balance drops to 0. And if I go withdraw another $500, I should get, you can't do that, right? You're overdrawn. But if you allow me to if I have $1,000 in my bank account and you allow me to withdraw $1,500, that's not a consistent system, right? So that's a place where you probably want to favor consistency over availability. So think about that for your apps. Where can you be more available and less consistent, and where can you be more consistent and less available? If you look at Kubernetes as an orchestration platform, Kubernetes eventual consistency or whatever, consistency, I can't even type, eventually consistent, yeah. So in Kubernetes, it's called like an eventually consistent system. When you make like a request to Kubernetes, it's not going to get done right then and there. It's going to get done when it can. And we call that eventually consistent. I mean, I think there's some good stuff. You should just look these terms up. All right, look up eventual consistency, look up strong consistency and eventual, all that stuff, and see what people say about them, because there's different like categories to this stuff. Okay, let's move back onto the book. Cool. So that was chapter 5, replicated systems. I'll quickly cover chapter 6 and then we'll call it. Chapter 6 is actually not that bad, so I'll go through it. Cool. So in chapter 5, we talk about having these stateless services and how we can replicate them behind a load balancer to scale up, to be more reliable, to be more redundant, to be more available, right? Now we're going to talk about sharding, right? So instead of like stateless services being replicated, we're going to have sharded services instead. So in the replicated services that we just saw in the last chapter, every replica of the service can handle every request, right? Because they all have the same logic and the same data. They can handle any request. Doesn't matter if I go to node A, B, or C, or 1, 2, 3, any replica can handle any request. In a sharded scenario, we break up the data for your application into these different shards that we deploy behind some sort of sharded service. Now though, each shard can't handle every request. Each shard can only serve a subset of the requests. And this will make more sense as we keep going down. In this example, if I have a replicated service, it doesn't matter if I go to node 1, node 2, or node 3. I'll get the same data from each one of them. In a sharded service, if I go to node 1, I might only be able to get certain request answers. If I go to node 2, I'll get different request answers. And if I go to node 3, I'll get different request answers. Why is this important? For 100 editors... Okay, yeah. Why is sharded services versus replicated services, why is it important? Well, sharded services is a way of breaking up your stateful applications. So replicated services are good for breaking up your stateless services and making them more available and making them more redundant. Sharded services are good for breaking up your stateful services, the things that actually need to store data and store state. The author says here, I think this paragraph is perfect. This like sums everything up so nicely. The primary reason why you would want to shard your data is because the size of your state or your data is going to become too large to be serviced by a single machine. Sharding allows you to like cut your data up into different shards, and that way you can scale it up better. Think of Google, right? Google probably has, I don't know, millions of users, maybe billions of users at this point, and those millions or billions of users have what, hundreds of gigabytes of data? You can't put all that on one machine. You can't put all that data into one database. It's impossible. You have a question? I don't know if that's a hand raise, Scar. Sorry.
I wanted to know how, like, by data, do you mean like number of requests?
I mean the data stored in your database, right?
Okay.
Yeah.
Okay.
Like if you're an application that, I don't know, stores, like if you're an API that stores Pokemon cards, yeah, if there's only like 2,000 Pokemon cards, you can store them in one database. That's perfectly fine. But if you have 2 billion Pokemon cards or like 2 trillion Pokemon cards, you can't really put that all in one database. It's going to get pretty slow, where you're going to hit some resource constraints. So you're going to have to start sharding that data into different ways. Maybe you break up your Pokemon cards so that Pokemon cards A through M are stored in one shard, and Pokemon cards, N to Z are stored in another shard, right? Maybe you do it that way.
Okay, and I understand now.
Yep.
And when do you know that your data is just too big to be in a replicated service? You have to shard.
When your data layer, like your database and your caching layer or whatever, when they are overloaded.
Okay, thank you.
Yep, when they get overloaded and they can't keep up with your normal traffic needs, it's time to think about sharding. All right. Cool. So let's talk about sharding. So when you shard, you have different parts of your data like split up across these different shards. And generally speaking, if you want to shard like your cache, you'll have like your user hit your application, and then you'll have like your cache sharded across. So not all of your cache is available on each shard, just a subset of your cache is available on each shard. right? So think of it like Pokemon cards, you know, A through F, F through M, N through Z, or whatever, right? Like they're in these different shards. In order for your application to be able to know which shard should it connect to for a given request, there needs to be some sort of service sitting in front of your caching or sitting in front of your sharding layer to know how to route the requests to the correct shard. Okay? And the author says you can actually use maybe an ambassador to do that if you wanted to. The author then goes into like, why would you ever want to like use sharding for any of your data? Like, why, right? Why would you ever want to shard your database? Why would you ever want to shard your cache? Why would you ever want to shard anything? And the author gives you some like math here. And he says, imagine that you have a caching system that has like 10 gigs of cache, right? And it can serve 100 requests per second. And let's say that our service has 200 like gigs of results that can be returned, and it expects 1,000 requests per second. If you wanted to serve 200 gigs of data over 1,000 requests per second, you would need 10 replicas of your cache, because 10 replicas times 100 requests per second equals 1,000, right? If you need to serve this many requests, that means you need 10 replicas for your cache. So you do that. You deploy 10 replicas of your cache as a replicated service. So each of your caching layers has the same data on it 10 times, right? But when you do that, like your cache can only hold a maximum of 5% of the total data that we want to serve. And to put this into different analogy, you have 200 gigabytes of Pokemon cards you want to serve, and you want to serve 1,000 Pokemon cards a second, right? If you deploy your cache as a replicated service, you'll only ever be able to cache 5% of your Pokemon cards, because each cache is holding 10 gigabytes of Pokemon cards. Does that make sense? So out of the total 200 of Pokemon cards you have, you can only ever have 10 gigabytes of it in cache at any given time. That's a 5% cache that you can have. That's what you would do if you did a replicated service. Right? And the author says like that's great for redundancy, but this is terrible for maximizing like utilization. If instead you took those Pokemon cards and you did a sharded cache, you can serve better, like you can serve more cache. And what he says is we're going to still serve the same number of Pokemon cards per second, or same number of requests per second. We'll have 10 shards. Each of them can serve 100 Pokemon cards a second. But now, since each shard in the cache has a unique set of data, we're now able to store 50% of the total Pokemon cards. Because each cache has 10 gigs of Pokemon cards, there's 10 of them. 10 times 10 is 100, and 100 is 50% of 200. So now we just got a 10-fold increase in cache storage because we sharded rather than doing a replicated service. Does that math make sense for anyone? Does anyone want me to kind of talk about that? It took me a second to understand it first when I first read it, like when I first read this book.
So in that second example, you just have no redundancy for your cache.
Exactly. But you saw the trade-off we made, right?
Yeah.
In the first example, we had a shit ton. I shouldn't say shit on YouTube. We had a crap ton. We have a crap ton of redundancy, but we can only store 5% of the only 5% of the total data could be cached at any given time. If we sacrifice some of that redundancy, we can store 50% of the total data in cache, right?
But you could also like meet halfway, right? Like you could have 3 or what is it, 6 of them, and it's like if you want to do 30% cache, you have each of them do 10% or whatever, right? Of
exactly.
Individual sets.
Yep, and and that's where we're headed. So you can see that clearly doing a whole replicated like caching sucks, right? We can only do 5% of the cache, like not worth it. But also doing a completely sharded cache gives me way better cache, like I can store way more in cache. But now I have a redundancy issue. If one of those cache shards go down, I lose the cache for that set of data. We can see where we're going with this. Combine the best of both worlds, right? shard your data, but each shard can be replicated. That's the ideal way. Obviously, that's more complex and whatnot, but that's where we're kind of going. And we'll talk about that in a second. Cool. And then the author kind of talks about like the role that having cache, and mind you, sharding your data is not limited to cache. You can shard data at the caching layer. You can shard data at the database layer. The author is just talking about cache right now, but you can shard any data. The author dedicates this section to talking about the role of like having cache in your system, like its performance. When you have cache, it's often like a order of magnitude faster than hitting your database. So there's that part of it, which we'll talk about, in the next, down here. But forget about cache being faster than your database or whatever. Forget about that for a second. This paragraph is super important. I want to read it. So imagine you have like your application layer, and your application layer can handle 1,000 requests per second, right? It can serve 1,000 Pokemon cards each second. After 1,000 requests per second, your system's going to start erroring. It can't take no more. It can't serve any more requests. Your system's going to start erroring out. If you threw a cache in front of this system that has a 50% hit rate, then you'll be able to increase your maximum request per second from 1,000 to 2,000. Why? Because your application can serve 1,000 requests by itself, and your cache can serve 50% of that. Okay? And if you get 2,000 requests that came into your service, 50% of them can be cached. The rest of the 1,000 can be handled by your service. That's the math behind this. Right? This case, cache is going to be super critical to your service, because if your cache fails, all that load is going to be redirected to your backend servers and they'll fall over. So instead of doing that, you should limit your your request per second to something kind of in the middle. That way you can sustain some cache failure and also keep your service up. So when you're like building applications and whatnot, you have to test this. How does my system perform with full cache? How does my system perform with no cache? How does my system perform with cache that gets deleted halfway through the load? Does my system fall over? You need to test all this out and find the numbers that work for you. Cool. And that's one area of performance, right? Requests per second is one area that you can do performance. There's another area of performance called latency, right? How long requests take to be served. And that's a big thing too. And the author says, imagine that your system can serve a request in 100 milliseconds, but your cache can serve a request in 10 milliseconds. That's a whole order of magnitude better, right? And your cache has a 25% hit rate. Now the average latency for your system drops from 100 milliseconds to 77.5 milliseconds. And all you did was throw a cache in front of the system. You didn't make any application changes. You didn't do anything else. You just threw a cache in front of your system, and now your average request latency is dropping. Your system is more performant. Okay, so these are some of the things you think about when you're trying to introduce caching into your setup. Okay, sorry, I know that was a lot. Any questions on that so far?
Yeah, what are, besides, sorry, I'm just gonna ask, what are some things that could go wrong when a cache fails, and how do you fix it?
Yeah. So if your caching layer completely fails, like caching is just no longer a thing, that means your application won't be able to connect to your caching layer. And instead, it now has to go to the database for all the answers to its requests, right? That's going to be higher latency because that takes longer. And it's also going to put more stress on your database because now your database is getting all that load directly rather than being offset by the cache. So your database can fall over, right? Your app can fall over because it's holding too many requests per second and taking too long to respond. All of that can happen. How do you fix it? You might have to scale the database up to make it handle more load. You might have to scale out your application node. You might have to introduce some sort of like delay into your application so that it has more time to process these things. It depends.
Okay, thank you.
Yep.
I'm glad it wasn't like a just complete project crash.
No, it depends, right? It depends on how it fails and like what else fails after it. But generally speaking, when one system fails, you can see a cascading failure of other systems, right? So if your caching fails, well, then now the load goes to your database, and that increases the chance that your database can fail, right? And so on and so forth.
Thank you.
Yep. And which is why all these patterns that we're talking about in this book, you can apply these patterns to different places in your application stack, right? Your caching layer can use replication and shards. Your database can just use shards, and your application itself can just use replication. You can mix and match these patterns throughout your application to get the benefits that you need so that you don't have these problems. You know? Cool. And then like what I said before, so you don't just have to choose one or the other. You don't just have to have a replicated system behind a load balancer, and you also don't just have to have a sharded system. You can combine them both into like a sharded replicated system that combines the benefits of both worlds. I'm just looking at if there's anything else I want to do here. Cool. Yeah, and the author gives you a little bit of a hands-on thing of how you can deploy like an ambassador in front of like a sharded cache. He uses memcache here as like the caching layer. He shards that cache, and then he puts a load balancer in front of it. Nothing crazy here. It's just like he just wants to show you an example. And I think he gives a diagram of this. No, he doesn't. Never mind. It's fine. I was gonna like make one of these examples work for y'all, but I just didn't have time, so I'm so sorry. But what he does say in here is that there's two ways you can expose. Let me go back up to that one diagram real quick. Sorry. Remember when I said you have shards? Each shard has just a subset of the data, right? So in order for your application to know which shard to go through, you need some sort of like thing in front of it to like route the request to the right shards. In the example, the author says you can either throw an ambassador in front of your cache or in front of your sharded service, so that way the ambassador knows how to like route the request correctly, or you could deploy a shard router in front of it, which is essentially like a load balancer. And there's trade-offs of using one or the other, so just keep that in mind. But either way, you have to have some mechanism so that your application knows which shard to connect to for a given request, right? So if I want Pokemon card A, I should be routed to the shard that can serve me Pokemon card A. But if I want Pokemon card, F, I should be routed to the shard that can serve me Pokemon card F. Cool. I don't know why I use Pokemon cards. It just came to mind. So my bad. I probably should do something different. Okay. Now, there's something about sharding that you need to know. Sharding doesn't just magically work. You have to be intentional about how you shard your data, right? You can't just be like, oh, I'm going to break my data up to 10 shards, and we're just going to like modulo over the requests. And if a request ends in 1, it goes to shard 1. And if request ends in shard 9, it goes to shard 9. And like, you can't just do that, right? That's not going to work. The author tells you why. Yeah, exactly. The author says, listen, if you have 10 shards and you want to take a given user request and map it to a shard, you need to use a sharding function to do that. And how it looks is you take a request, you pass it through the sharding function, and you get the shard that you should be connecting to for that request. Okay? Generally speaking, the function that you use for sharding is just a hash, and then you use the modulo operator to like limit to the number of shards, right? You know that like if you take any integer number and you modulo 5, you'll get a number between 0 and 5, right? Similarly, if you take any integer number and you modulo it with number 7, you'll get an integer number between 0 and 7, right? So this allows you to identify a shard that you can connect to. The sharding function that you choose has to be deterministic and uniform, okay? It has to be deterministic in the aspect that every same request should always go to the same shard, right? So if I want Pokemon card A, I should always be redirected to shard A to get that Pokemon card. And it should be uniform. The distribution of my data throughout the shards should be relatively even, right? I shouldn't have a shard that has more data on it than the other shards. If I do, that's called a hot shard, right? Hot sharding. This is actually, it works kind of like a hash table. Yes, exactly. And we'll talk about that in a second when we talk about selecting a key. But I want to talk about hot sharding, right? If I have Pokemon cards sharded, and let's say I have 26 shards, right? I have a shard for each of my Pokemon cards that covers every letter of the alphabet. So if a Pokemon card starts with A, it goes to shard A. If a Pokemon card starts with F, it goes to shard F, right? So on and so forth. A hot shard would be a shard that has an unfair or uniform number of Pokemon cards or data compared to the other shards. So let's just say, for example, that out of all the Pokemon cards in the world, majority of them begin with the letter A. Well, then in my example, my A shard will be very hot compared to the rest of the shards because it'll have an unfair number of data compared to the rest of the shards. That's a problem, right? To give it more realistic terms, imagine that you shard your users for your website. Like, imagine your Twitter. And you shard your data based on the username, right? So usernames, with a certain character string or whatever, go to this shard, and usernames of other ones go to other shards. Now imagine if you have multiple celebrities with the same or similar username that all get sharded to the same location. You just introduce hot sharding into your system, right? If Taylor Swift and Beyonce and all these other famous people all get sharded to the same location and their tweets get millions of views or whatever, you're just heating up that shard, right? So you need to think about that when you're designing your applications and how you can best comment that and keep your shards uniform across them. You are always going to have hot shards, always. You just have to limit it, okay? Any questions on that and why that's important? No, Matt, everything's great. We love you. All right, cool. And don't worry if some of this is not making sense, whatever. Again, we're just learning patterns. You can always come back and read the 10, 15 pages of these chapters and see if you understand, right? Don't worry about it. This is not oh my God, if you don't learn this, you're going to be left behind. You're just getting introduced to the patterns. So don't worry so much. You're just that good of a teacher. Thank you. Cool. So you've decided that you want to shard your data. You've decided that you need to take these requests, pass them through a hashing function, and get a shard back. What is the key that you're going to choose to shard that request, right? Let's say you have a web server. If you have a web server, you can shard things based on the time of the request, based on the source IP, based on the path that's being requested. And if you do that, that sounds good on paper. And if you do that, imagine you get a request that comes in at 12 o'clock from IP 1234 and it requests, some file. That will get sharded to one shard. And let's say the next minute, another request comes in at 1201 from IP 5678 and it also requests the same file. But that gets sharded to a completely different place. In your head, you should be saying wait a minute, why are both of these requests getting sharded to different shards? They're requesting the same file, right? You need to choose a key for your sharding that routes your requests to the right shard without introducing these hotspots. So you need to be intentional about what key you choose. So given this, you might be okay, I'm going to change my key and I'm just going to shard based on the file path that's being requested, right? Let's say you do that. That would work, but now you run into different problems. sometimes the client IP is actually important, and you do want to shard based on the client IP, because you might want to look up the geographic region for that user, right? Like if it's a French user, you might want to route them to the French page, and if it's a user, a United States user, you might want to route them to the English page. So in this case, maybe you don't shard based on just the request path. You would just shard based on the IP and the request path. Even that's a problem, because now what if you have two French people with two different IP addresses? They'll also get mapped to different shards, which will result in like hot sharding. That's going to be too specific of a key to use. So you need to find the key that's going to work best for you. And in this example, the author says, instead of doing the IP and the path, you do the country that the IP comes from and the path. And that gives you a Goldilocks sharding key. It's just right? Not too cold, not too hot. It's just right for your use cases. When you're doing sharded data, you need to think about all of this. And you need to choose a shard that's just right for the patterns of data that you're going to be serving. Any questions on that? This is hard. I'm not going to sit here and tell you that this is easy and that you just do it and oh my God, this is hard. And it changes over time, and you have to constantly be measuring and seeing like, am I doing this correctly? So I'm not presenting this for you to be like, oh, it's just easy, just choose a sharding key. It's hard. You have to know your data. You have to know your users. So just keep that in mind. Is there any rule of thumb for choosing the right key? Not really. It's just about, are you like, you can choose too generic of a key if like, I guess you can choose too generic of a key if you'd like, and like have shards that have like a bunch of different data on it, but might not be so useful. That's fine. Or you can choose too specific of a key and then have like more hot shards, essentially, like data that's replicated across shards. You can do that. Both of them are fine if you're okay with the trade-offs. I guess what I'm trying to say is like, there's no rule of thumb. Just be okay with what happens if you choose too generic of a key and too specific of a key. Just be okay with what happens if you do that. That's the only rule of thumb. I need to put my hands on the keyboard to cement my understanding. I get the concept. I know. It's hard. Sharding, this is a hard topic. I don't expect like everyone to be like, oh my God, I get it. It makes so much sense. I could do it tomorrow. It's tough. There was like I have to find the resource, but there was like a database sharding resource that you can look at that like helps you spin up a MySQL table and like shard it and see how it works. I have to find that again. Yeah, Nia, I think you had a question, right? Yeah.
So let me formulate it in my brain for a second. So I'm assuming there's tools or like procedures that you can use to basically like stress test your stuff. So like if you know like where your users come from primarily, like let's say you have like historical data, it's like, oh, we get X number of users from the US and Y number of users every day from like the UK or whatever.
Yep.
You could just like stress test like based on whatever configuration you decide for your shards, and then like you can pick which one's best and then like adjust, I guess.
Exactly.
Because that would be like that'd be the only way I could think of to like actually
Exactly. That's exactly
like
it.
address it, because you can't like just deploy it and like hope. You'd have to like constantly change it, I guess, depending on like how your data changes.
Exactly. You need to know your data, how it's being used and accessed, what your current key is, and like so you can know if your current key is too generic or too specific, and then just adjust as necessary. And like you can deploy like little POC environments that like run a certain type of load through it and see how it affects your sharding, and then do it again for a different data set and make decisions based on that.
Right. Is it common to like run like a parallel service that you just like take the traffic that you're getting and just say like, hey, go to this sharded service and we'll just see like how it goes for like
we kind of spoke about that in part 1 where we said, like, I forgot if it was in the ambassador somewhere, but I think it was like one of the sidecars where it's like duplicate the service, like duplicate the
Yeah.
this one, request splitting down here, right? Using an ambassador to do experimentation or request splitting. There was a chat in chapter 3, we talked a little bit about that. And that's what would be a good example of what you're saying. Have some sort of ambassadors, have some sort of logic that takes a request, passes it to the production environment, but also makes a copy of that request and sends it to a different environment so it can do some experimentation and see how it would affect my sharding. That would be a perfect example of that. And that if you think that Netflix is not doing that to your request right now, they are, right? We're not all getting, if we all go to netflix.com and like load a movie or whatever, we're not all going to the production Netflix environment, right? Some of us are actually going to a staging environment. Some of us are going to an experimentation environment. We're all going to like random environments in the Netflix stack, and they're running experiments on us right now, right? Same thing with Google, same thing with Facebook, same thing with any of these places, Twitter, all of them. They're running experiments to see like, hey, I've just deployed this new UI refresh. 5% of my users are going to get it. You might be in that 5%, right? So this happens all the time. Maybe not always just for sharding, but it happens all the time, right? Cool. And then the last few bits of this chapter. So selecting a key is super important, right? We talked about that. You don't want too generic of a key and you don't want too specific of a key. So we talked about that. What's also important is choosing a consistent hashing function, right? And this one, I think, is a little hard to follow the math at first, but let's walk through it. If you have 10 shards, right? You have 10 shards. And if you map your data onto those 10 shards, your data falls the way it falls, right? Now let's say you wanted to go from 10 shards to 11 shards. What happens to your data now? Well, now pretty much a large number of all your data is going to have to be remapped to a different shard than it was before, right? Because modulo 10 is quite different than modulo 11. So the number that modulo 10, went to one shard, if you take that same number and now modulo 11, it's going to go to a different shard. So you see that remapping happen, right? That's a problem, actually, because when you do this, you're going to have a very large miss rate until your shards are repopulated with the new data. We call this resharding, okay? To limit the blast radius of this resharding, we use what's called a consistent hashing function, okay? And all that means is it's a special hash function that are guaranteed to only remap the number of keys over the number of shards of data. So for example, when you move from 10 shards to 11 shards, we're only going to remap less than 10% of the keys, which is, the number of keys over 11. That's it. So instead of having to map like maybe 60+% of the keys, we're going to remap less than 10% of them. That's what consistent hashing means. And I want to show you a graphic real quick. Consistent hashing image or something, because it's usually drawn as a circle. And I think the circle is really cool. You can see here, I don't know if this is the best one. Maybe this one's better. Yeah, this one's kind of better. So you can see like consistent hashing is kind of like, looks like a circle almost. And you can see here that in this example, I have two nodes, right? Node A, node B, or it's probably better with a bigger one. I'm trying to find one that doesn't have anything crazy in it. Doing this live is always fun. This one's fine. We'll do this one. So you have like you have your two different shards, right? Two nodes, and where they are, like wherever you are on the circle, wherever your hash goes, you're going to use the next node for the data. So in this case, we have what? I think 16 nodes. Yeah, 16 nodes. So wherever you land in this circle, you'll use the next node like that's in front of you. So if my data happens to land right here between 0 and 1, I'll use node 1. Okay? Same thing here. If I land between 2 and 3, then I'll use node 3. What happens when you use such a consistent hashing algorithm? Well, let's say I removed node 0 from the equation. I got rid of it. Now what happens is the keys that were stored on node 0, which are the keys between 15 and 0 here, node 0 is not there anymore. So all of those keys have to now be remapped back to node 1, because that's the next node in this circle when we follow it clockwise. So that's only a subset of the keys, right? That's only these small little subset here, which is number of keys divided by number of nodes. So that's much better than changing your modulo and having to remap almost everything. So I hope that makes sense. This took a minute for me to understand too. I would definitely recommend you all read up on it and see why that matters. But I hope that the graphic probably shows you like why that's important. So instead of having to remap like randomly, you just remap this small section of keys that got affected. Okay. Any question on that?
Sorry, yeah. It's actually pulling it because it's like, I think I see it like the pattern. So it's like when you're incrementing your denominator, your number of shards, it's always going to offset, what is it, like 1 over the number of shards you had before?
Yeah. Or
right?
It's
going to
over the
offset
number of
that
shards.
number. Yeah.
Yeah. K being the
And
number
so
of
like
keys.
if you had like 50 as your number of shards, if you move to 51, wouldn't it offset? It would offset like 50 of those.
If you had
one.
Yeah.
Sorry.
No, it's fine. It's based on the number of keys. So let's say you had like 1,000 keys spread across 50 shards, right? So that, you know,
so it'd be 1/50th.
Yes, exactly. In the optimal case, if you have 1,000 keys spread across 50 shards, that means each shard roughly has 20 keys on it. I say roughly because you could have hot shards, right? Like roughly.
Yeah.
Right? But if you go to the 51st shard for those 1,000 keys, then you're only going to have to remap 19 of those keys, which is 1,000 divided by 51.
Yeah.
That's much better than having to
out
map
all those that change, and it just like pushes them to the end
to the
like
next
your
one.
New hash function.
Exactly.
Number of shards.
Yep. And what's really going to happen is like, so keeping in line with this graphic that I have in front of me, let me make it bigger, I guess. Keeping in line with this graphic I have in front of me, let's say I have hashes in between 15 and 0, right? These hashes here, these keys, right? This data, when I eliminate node 0, when I get this shard out, like maybe it's corrupted, maybe something's wrong with it, when I eliminate it, I drop from 16 nodes to 15 nodes. So all of these keys in here now have to be served by node 1, right? Node 1 is going to pick up the slack for me. What does that mean for my application? That means if data comes into my application and it shards to this area, it's going to get a cache miss, right? It's going to get a miss. And it's going to recalculate the shard and store it on node 1. That's what's going to happen. But it's only going to do that K over number of nodes times in the worst case, which is far better than just doing the modulo and having to do it like a very large number of times. That's all that this consistent hashing means.
What's the difference between the two things you just said? You said like one, like it picks one, right? So it's like, oh, it goes to 0 and then it goes to the next one. Are you saying it just like increments instead of doing like the modulo?
Yeah, I need to be able to draw on this. What's the one? Excalidraw? Yeah. Maybe I probably have something. Yes! I don't know what this is. I love it. What a good, can I just clear this whole thing?
Probably click and drag.
There you go. Yeah, let me just draw real quick because I think it's better if I draw it. Right, you have a circle, which I probably should have made with the circle tool, so I'll do that. Yes. Why does that look so weird? Is it like a hand-drawn circle?
It tries to do hand-drawn, yeah.
Oh, okay. Let's say I have a circle, right? And I have, different nodes on the circle. And I'll just draw 4 of them, right? So this would be node 1, node 2, or shards, right? Shard 3, shard 4. I have these shards. So let's say this area right here is these keys, these red keys, they get stored on node 1, right? These green keys get stored on node 2. These blue keys get stored on node 3. And these orange, that's probably a bad color. Orange and red looks familiar, whatever. These orange keys get stored on node 4, right? That's how it works normally. Where's the drawing? Right there. So that makes sense, right? So if I have like Pokemon cards or data or whatever it is, if the data falls in this red range, it goes to node shard 1. If the data falls in this green range, it goes to shard 2. If the data goes in the blue range, shard 3, orange range, shard 4. That make sense?
Yeah.
So far? Okay. Now let's say I need to eliminate node 1 from the whole equation, right? I need to like, this goes down. Or I need to get rid of this. I'm scaling down from 4 shards to 3 shards or something. What happens? Well, what happens is now the red area was stored on shard 1. Shard 1 is no longer in existence. So anything that gets sharded to the red area now has to get sharded on node 2. So what is your application going to do? Your application, let's say like app, right? Your application's out here. If it wants to like request data from this shard, it's going to no longer see that data, because when it does this with node 1 out of the picture, it's going to try to hit node 2, right? And node 2 is going to be like, hey, bro, I don't have that data yet. That's a miss. So the application will do a miss, and it will reshard it and actually store it on node 2 this time, right? So you could imagine that like it was this Pokemon card right here that I did that for, right? And then I do it again for whatever's in here, and I keep doing it, and I keep doing it, and I keep doing it. And eventually what's going to happen is node 2 is going to actually have all of these keys now at some point in the future.
Right. So what did you mean when you said it doesn't get moduloed? Because doesn't it, like, you modulo the value based on the number of shards to pick the node it goes to originally, right? So
Yeah.
still do that. Like whenever your app does it, it does the modulo and then it hits the value that was in node 1, and then it's like, okay, then it cache misses, but it still does that initial modulo, right?
It's more of a module, but now it's a module with ranges. That's why like this is drawn this way, right? So we're no longer storing directly, like we're no longer modulating to 1 or to 2 or to 3 or to 4. We're modulating to some random thing, and we're mapping these nodes to map over these range of values. That's all that really is. Again, it's more of like, it's more in depth. So it's probably better if you like read a dedicated resource on it, because it is a little bit more than depth to that. I think some of these probably like explain it better. Some of these resources. Again, I didn't think that I was gonna cover this in like depth today, so I didn't like prepare any of my stuff. But read up on this, because it does still use the modulo, but basically each node is mapped to a range of possible module values in this case. So, yeah, read up on that a little bit more. I think there was a really nice resource, and I forget the hell where it is. I think it was on, I think it was like an system design resource. I forget where it is. Yeah, I'd have to find a resource for you. But yeah, I'll have to look it up and see if
I'll
you.
find something.
But basically, like, I think this probably gets it better. See how, like, you know, from key 0, like from 0 to this, it goes to this node, and then from these keys, it goes to that node. Like, it's a range of values in this time. So it depends on where it falls in the range of values. The next node will be where it gets stored for real. So that's kind of the idea.
But the ranges are adjustable. Is that what changes? So it's like you can say, okay, well, node 1 is, you're useless now.
Yep.
You don't have a range 2. You take that range, and then it just,
yeah, I guess
like the modulo still works. There are modulo, right? It still fits it in a range.
Yes.
But you're adjusting the range of a node, and you can tell the algorithm that or you don't even have to tell the algorithm. It just does its calculation, and then the node knows what its own range is.
Yep. This, I think, explains it pretty well. So before, we were doing the modulo based on the number of nodes or based on the number of shards, right? We would do like hash code module number of nodes. That's what would be our shard. In the consistent hash function, you would do hash code modulo the range on your ring, right? That's the idea. And that'll put you somewhere on that ring, and then the node that you actually use for sharding is the next node on the ring, right? The next node that you run into on the ring. So I'll send you all this so you can read up on it. Again, this is a tough topic, man. I'm not gonna lie to you. When I had to read this a few times before, I was like, oh, I get consistent hashing. I understand. So I'll send you this resource. I don't know if it's the best one, but reading any resource is probably better than nothing.
Yeah.
Geeks for Geeks is probably good too, but they kind of get a little weird sometimes. I don't know. I don't like them for everything. But I think
it's hit or miss.
Yeah. I think the one I saw was from Alex, the guy that does he does the system design training. Like he has a pretty popular system design course. I think in his course, am I gonna get in trouble for streaming this? Maybe. I think he does design consistent hashing, and I went through this. Yeah. This is where I looked at it. This is paid though, so I can't give this to you. But this is where you have a range of possible values and you kind of connect them like a ring. Does that make sense? You kind of connect both ends to each other.
I think I get the concept now. It's
Yeah. Sorry, I know that was a little much. It's just that's the idea. And then you put the nodes on that ring. So nodes are mapped into different locations, and then depending on where the modulo maps to that ring, it's the node that you use. Yeah. And that's what makes this hash consistent versus just modulo number of nodes. Okay, I'll send this link to you all anyway, just in case you do want to sign up for this or whatever. And this is the direct link to that. It's not gonna be meaningful to you if you don't pay for it, but I'll just send you the link anyway. That way you have it. Okay, sorry, back to the things. So consistent hashing is important because you don't want to have to remap a ton of your keys to different shards. You only want to map a very small subset. So when you use consistent hashing, you're guaranteed to remap K over shards keys, where K is the number of keys and the number of shards that you have. That's what consistent hashing gives you. And that's why it's super important. Okay, any other questions on consistent hashing? I'm not going to go through the hands-on part. I'm just going to skip that. And then the last page is just two small concepts. Cool. So as I said before, it's not an either or, right? You don't have to just use sharded services. You don't just have to use replicated services. You can implement both, where you can do replicated sharding services, and that works pretty well. And that's what the author is saying here. So I already kind of talked about that, so I won't talk about that. And then we'll just briefly talk about hot sharding, even though we kind of been talking about it this whole time. No matter how you shard your data, there's always going to be certain shards that are hotter than the other ones because they have more data sharded to them than others. And that's just going to happen, right? You can't choose a perfect sharding function. You can't choose a perfect sharding key. It's never going to happen. There's always going to be organic traffic that just makes hot shards, right? And I told you the celebrity problem where maybe multiple celebrities, since you were sharding based on location, and there was, I don't know, some sort of Grammys or some sort of event happening and all the celebrities went to one place and your location-based sharding heated up, or you were doing username sharding and most of the popular celebrities begin with username A or something and they get hot sharded. There's always going to be hot sharding in your system. You just need to know what to do when that happens. And the author's saying here, if you have a sharded system that's, relatively equal, shard A, shard B, shard C, and shard A starts to heat up, right? That's why this fat arrow's here. You have options. You could either scale up shard A and make it replicated, or you can decommission shard B, move that to where shard C was, and give shard A more of the ring space to use for its sharding, right? And replicate it over. So there's options that you can do here, and that's all the author's saying is just be mindful of hot sharding because you're going to need to account for that. And finally, we're done. Sorry, I didn't mean to go over by this much, but we kind of did. So yeah, any questions, comments, or concerns before we call it today? If you take nothing out of this, except for if you take nothing out of this, just take this out. If you have stateless services, you can use replication to scale them up or to account for more nodes, right? Or sorry, more load. So stateless services usually use replication, and stateful services usually use sharding, right? So if you take nothing else out, just take that with you, and it'll make sense in the future when you have a place that like you think about those problems. Cool. And you can always ask questions, right? Like, again, and I really want to stress this is not about like, oh my god, I'm an expert in replicated services and sharded services, I'm gonna deploy it tomorrow. This book is just covering the patterns, right? So you should just recognize that these are patterns that you can use, and when you ever run into this in your career, or when you ever face a problem that has to deal with these things, you should be able to look at these patterns and see if that can solve your problem. That's it, right? We're just learning about patterns here. Cool. Any questions, comments, or concerns?
I have a quick question.
Yep.
For example, in sharding, where do you implement that? Is like as a script? The logic.
Yeah, so it can be something as simple as, let's say you want to shard your database, right? It can be something as simple as I'll deploy 3 different databases, right? 3 different database servers, and they all run the same, like they all have the same database tables in them. And then you have some sort of proxy service or something sitting in front of the database that takes the database requests, does the sharding operation, and sends it to the right location, right? It could be something as simple as that, or it can be as complex as like, oh, I want to shard types of data, right? So like I'll have a certain subset of my data over here and a certain subset of my data over there, and the application knows how to send data or how to send requests to those subsets, right? So there's no middleman in between your application and the sharded service. Your application has that logic built into it, right? But something has to have the logic that knows how to map a given request to a given shard, and then something has to have the logic to be able to shard the data itself. Modern databases have sharding usually like built in if you want it, but managing it and whatnot is a more complex topic, but it's kind of there. But for something like Redis, I don't know if Redis has like sharding kind of built in so much. Maybe it does now, but I don't know if it did forever. And in that case, you would probably throw like a load balancer in front of it that knows how to shard for it. And that's what the author did in this. That's what the author did in this book.
Yeah. Yeah. Makes sense. Thanks.
Yeah, no problem. Any other questions, comments, concerns? And mind you, I'm not going to sit here saying I'm an expert at all these things. I'm not, right? If you ask me to go spin up a sharded system right now, I'll have trouble doing that. It's tough stuff. It's more of just being aware that these patterns exist.
Yeah, I was reading.
Say it again?
No, I was reading this sharding stuff on the AWS, one of the white papers. So they had lots of scripts. So I didn't know where would this go. Like example scripts were there.
Oh,
That's
yeah.
why I asked you. Oh.
Yeah, Amazon's example scripts are kind of annoying sometimes, because like they don't like work. They're just kind of like pseudocode.
Yeah.
I ran into that today when I was using AWS or something. I am going to share this resource though. If you do want some good reading on like system design things, there's this popular system design primer, and it talks about this stuff. So you can see like there's a whole sharding section, and you can read more about sharding as well. And they link to other resources. Oh look, there's a consistent hashing resource you can read. So they link to other resources that you can read to learn more about sharding and how it would work. So this is a very, very good GitHub repo. You should probably like star this and have it in your stuff. But
Thank you.
Yeah, no problem. Scar, I know you said something before. I think it was you actually.
I think it was a joke or something.
Oh, that like if I don't know how to do it or whatever, like.
After you said that, you were like, "Oh, I'm not an expert." I'm like, "You sound like one."
I just read up on it.
Like this was a very thorough explanation, and yeah, you did a good job teaching us.
Oh, thank you. Thank you. Yeah, it's tough stuff. There's tough problems, but just know that like this is how the big companies of the world are actually operating today. And I think this graphic here, oh, I didn't mean to do that. I wanted to just open this up. Yeah. See, this graphic here kind of explains sharding pretty well in a graphic, right? This is kind of what I was talking about with the Pokemon cards. This is a very, very, very simplified case of sharding right here. Just store all the customers who from A to M on this one and store all the customers from N to Z on that one. And as long as all the applications know that that's how the data is stored, you're good, right? So cool. All right. For next Thursday, we're going to go to 7 and 8, chapter 7 and 8, where we'll discuss scatter gather, which is just a pattern for like, handling more requests per second and whatnot. And like we'll cover functions and event driven processing as well. And I think this one's is it a little bit of a big chapter? How far is it? 91, 81. Okay, no, that's only 10 pages. I want to make sure I'm not giving you a shit ton of pages to read. 73 to 79. Yeah, okay, it's good. So about 20 pages for everything. Yeah, so we'll cover chapter 7 and 8 next week, where we'll talk about these things and then go from there. And after that, we'll only have 4 more chapters left. So I plan on ending on the 29th. Sorry, 26th. I can't math, right? What's today? Yeah, 26th. I plan on that being the last day of the book club. Yeah, cool. What time do you usually start? 8 o'clock. Everything is in the book club channel. I'll be posting it all in there. I'll place that in Discord. We start at 8 o'clock every Thursday. And yeah, this book is very short, so we'll be ending on the 26th. So yeah, if anyone has any questions, just let me know. I'll be happy to chat more about this stuff. But I hope you are learning some stuff. And I hope you're just like seeing how this works, right? Like I know up until now you've just been primarily, running your Express apps locally, or maybe deploying it to like Railway or Fly.io or whatever you're using. And that's great. But just know that these patterns exist and they'll help you scale up as your application increases use, or as you have to like deal with more load, right? Holidays are coming. So Black Friday, Cyber Monday are right around the corner. These patterns are used during those times to handle that load, right? You don't just magically handle the load of Black Friday or Cyber Monday. You have to design your system to handle that load. And the patterns in this book help you like handle that load. Cool. All right. With that being said, I think we're good. Any last minute questions before we call it? No, Matt, everything was great. You're great.
Thanks,
Matt.
Matt.
Everything's great.
Yes. Awesome. And yeah, sorry that I didn't have examples ready for you all today. It has been a very busy couple of weeks for me. So I am so sorry. Tomorrow will be my last day at work and I'll be starting a new job soon. So it's just been I've been busy and I've been going to a conference every week. So yeah. Cool. All right, everyone. I'm going to end the stream. Where's my OBS?